Graphs. This video is going to look at graphs. In physics, as in most sciences, a graph can be a really useful tool. So we are going to look at graphs of position, velocity, and acceleration in one-dimensional motion. First, position. A position graph looks like this. I've got position on my vertical axis. I'm going to measure it in meters. It could be kilometers, feet, miles, whatever. And time on my horizontal axis, I'm going to measure in seconds. There are plenty of ways that one might move, but we are sticking in this course, for the most part, to constant acceleration. There will be a couple of exceptions where we have non-constant acceleration, but when those come up, I'll point them out very specifically. So under constant acceleration, there are a few possibilities. The simplest is that you just stand still. I've got somebody that's right here, and I'm just going to stand still. Time's going to keep going by, but my position is not going to change. It's a pretty boring graph. Shows up as a flat line. Next, maybe I am moving at a constant speed. So at a constant speed, maybe in the first 2 seconds, I cover a distance of a meter. Let me draw it this way actually. I'm going to start here, and maybe in my first 2 seconds, I cover a distance of 1 meter. In my next 2 seconds, I cover a distance of another meter. 2 more seconds, another meter, and so on. I get a velocity, or I get a position graph that looks like this. I'm moving at a constant speed. I can also look at speeding up. So here is a speeding up case. I'm going to start from some spot, and in my first 2 seconds, I'm going to cover 1 meter. In my next 2 seconds, I'm going to cover 3 more meters. 1, 2, 3. 2 more seconds, I'm going to cover 5 more meters. So what I end up with is a graph like this. It's a parabola. I could also have one where I'm slowing down. So maybe in this one, maybe at first I'm covering 5 meters in my first 2 seconds. So first 2 seconds, 5 meters, 1, 2, 3, 4, 5. The next 2 seconds, maybe I'm only covering 3 meters. The next 2 seconds, maybe I'm only covering 1 meter. I get a graph that looks like that. It's actually another parabola, but this one's upside down, or it opens downward, is the way that you might say that. Different ways of representing position for different motions, but you can see what these graphs look like. So now I'll look at velocity. So first I do want to address something. In one-dimensional motion, velocity and speed are really similar. Speed is the magnitude of the velocity vector in general, but when your velocity vector is limited to one dimension, that means the velocity can point in positive x or in negative x. So for 1D motion, a lot of times you'll see speed and velocity used interchangeably. A velocity graph looks like this. I'm going to draw it directly underneath. I've still got time on my horizontal axis, but now my vertical axis becomes velocity. you might see the units on velocity and think to yourself, hey, wait a second. That's what the units of the position versus time graph would have been if I found a slope, right? If I did a rise over run here, I would have had an x in meters over a t in seconds, meters per second. That sounds like a velocity, and you're right. Velocity is the slope of the position versus time graph. So this is velocity. I'm going to draw the velocity curves for each of these position curves and make sure to match the colors. So the standing still curve, that's easy. In the first 2 seconds of motion, I have moved nowhere. In the next 2 seconds, I have still moved nowhere. I'm going to get a flat line. And it is a flat line on 0. The second curve was for moving at a constant speed. This is the dark blue curve. Now the position kept increasing with time, but it increased at a steady rate. So the velocity must be a constant value. I could have, in this case I was going 1 meter every 2 seconds. So I would have a constant value, maybe like that. Or if I were moving faster, I might have a constant value like this. Now I don't have to be moving to the right. I could be moving to the left. If I were moving to the left, so if this graph were instead like this, I would have a constant velocity that looked like that. The green one. This was for speeding up. In the first 2 seconds, our position is increasing, but we're speeding up, right? So we are starting off moving slowly, and then a little bit later we're moving faster, we're covering more ground. Later we're moving faster still, covering more ground. We are going to get a velocity curve that looks like this. As time goes on, our speed, the magnitude of our velocity, keeps increasing. The slowing down curve, that one we started with some positive velocity. We started pretty high, and then we're going to get to this point where we are slowing down until we got to that point and came to a stop. Now if we had kept going, then what we would see here is we would start to fill out the second half of that parabola. At the 0 point, at the 0 velocity point, that means we are no longer moving. We were moving in the positive direction, but slowing down. Then we get to this point where we cross velocity equals 0. So in that moment, we are not moving for just a second. And then after that, we're moving in the negative direction, which means we have turned around and come back. The 0 point on the velocity graph is our turnaround point. And that's going to hit the peak of our parabola. I'm going to give you one more, and it's the acceleration graph. The acceleration graph is going to be pretty easy. I'm going to keep time on my horizontal axis, and I'm going to put acceleration on my vertical axis. And you recognize again, the units are what we had before, meters per second divided by seconds. So these are slopes again. First, the light blue line where I was standing still. It was a boring graph before, it's going to keep being a boring graph. Next, constant velocity. This is a flat line. I am going at one velocity. Acceleration is the rate of change of velocity. If my velocity is not changing, that means my acceleration must be 0. I would draw those directly on top of each other, but then you can't see them. So that's another line right on 0. Next up, the speeding up graph. I was speeding up, but my speeding up had a constant slope. This graph has a constant positive slope. So I've got a constant positive acceleration. And finally, the slowing down graph. I have a constant negative slope. I have a constant negative acceleration. Another flat line. My acceleration versus time graphs are admittedly kind of boring, but that's not the worst thing. Here are all of my graphs put together. I do want to give you a bit of a way to remember these too. So assuming that we're looking at constant acceleration, and like I told you, we're going to be in this course unless I very, very specifically tell you otherwise. We have a position function that looks like this. X initial, V initial t, half a t squared. So we can look at the different possibilities and kind of cross off what we need to, right? If we've got a situation where we say this is moving at a constant velocity, there's an acceleration of 0, I can say, all right, constant velocity, I can cross off this last term, and I will be left with x final is x initial plus v initial t. What I want to do is look at the highest exponent of t remaining in my position function. So let's do that first one first. If I've got this, so this is a 0 acceleration constant velocity situation, the highest exponent of t is t to the first power, so it's a 1. If my position function looks like t to the first power, my velocity will look like t to the 0 power, which is a flat line. T to the first power, that's a diagonal line. Diagonal line. And then my acceleration will equal 0. If the one above it's already t to the 0, then my acceleration will be 0. If I don't have that term missing, so if I have like the whole thing, right? X final is x initial, v initial t, half a t squared. In this one, my highest power on t is right here, is a t squared. So my x looks like a t squared. That's a parabola. My v will then look like a t to the first power. I'm just going down a power, so that's a diagonal line. And then my acceleration will look like a t to the 0 power, which is a flat line. If I were looking at the standing still case, then my x is just x initial, right? My x looks like a t to the 0, which is a flat line. And as soon as that is a flat line, as soon as that is a t to the 0, that means my v will be 0, and my acceleration will be 0. So I can take the power of my highest t value, use that to be my position line, And then from there, just say -1 gives me my velocity power. -1 gives me my velocity power. -1 gives me my velocity power. -1 more gives me my acceleration power. Gives me my acceleration power. And as soon as I've got something that's at t to the 0, everything below that is just going to be 0. That's how I'm going to tie those together. That's how I'm going to look at position, velocity, and acceleration. I'm going to zoom out just a second to hold those together. But hopefully that is a good way for you to be able to remember.